So our next speaker is Lisa Windham-Myers from the USGS.
All right. So I want to thank the organizers for inviting me to give this talk, new things that we've learned since we started some syntheses projects. I also definitely want to thank Ray for setting me up so I don't have to do all the pieces. I'm just going to do the little piece of the puzzle that I do. And I do that with a much larger community effort than just me. And I'm going to talk about it across the whole conterminous U.S., so the whole U.S. Basically, again, I'm representing a lot of different people, a lot of different efforts. What I'm mostly going to cover today is this NASA carbon monitoring system results we've had so far. There's 18 PIs. Everybody's contributions are huge. I'm just going to represent some of the sort of most germane things. There's many, many collaborators. There's a community effort to get people to share their data, and lots of people shared unpublished data. We're so thankful. The Soccer 2 chapter is going to come out this year. Ray is one of the science leads on the entire thing. I'm one of the lead authors on the Tidal, wetlands, and estuaries chapter, so I'll just share with you some of the insights from that. And then finally, I want to acknowledge the USGS Land Carbon Program, which has really pushed forward on coastal wetland carbon cycling, and also a group at the Commission for Environmental Cooperation, a tri-national agency that spearheaded blue carbon work across the whole North America. So here's a map that CEC came out with. And you can see basically this fringe of coastal wetlands. You can see mostly that the salt marshes in yellow are in the north. In the Mexican coastlines, we have mangroves, and then there's seagrasses all over the place. So this fringe map sort of underestimates how important this little land-ocean margin is. It's integrating a huge network of veins of flows across the U.S. And this is the National Hydrography data set. It was made into a really beautiful map by a fellow at Google. But it just, if you dig in, you can just see all these flows moving out towards the coasts. And what's interesting is if you think about it, this term terrestrial aquatic interfaces, TAIs, this is something that DOE has been pushing forward on. The idea is that all of these little interfaces that happen, they have more in common with each other than they do eco-regionally, let's say. The rivers themselves or the interfaces themselves have more in common because of that context. And so of all these different types of terrestrial aquatic interfaces that we can consider, all of these on the bottom are the coastal ones that they emphasize. We need to get away from thinking about this just pipe of things moving from the land to the ocean, but rather there's all these exchanges that are happening at that terrestrial aquatic interface. And those kind of things, if you really get into it, there's a lot of repositioning of carbon throughout the system as fixed carbon makes its way down towards the coast. That was tried to be captured actually in the new Soccer 2. And this is an overview of all the fluxes that are in here. This is Dan Hayes. I'm probably presenting this a little early, but the point is that tidal wetlands are definitely in the system a net sink. We know that. It's not the biggest net sink, but they're definitely taking up more carbon than they're losing. Also, this lateral flux, this is at a continental scale, is not minor to estuaries. And here is the lateral flux from all the land ecosystems. And so, it's basically about 6% or so. It's not minor. And I think it's an important pool that we should be following, tidal wetlands, how much they're fixing, how much they're releasing. And I think one thing you'll find out today is I think we have a pretty good handle on how much they're storing. It's not as variable as I think we've thought it has been. So the baseline that we're going from to understand this has a long history. People have been studying carbon cycling in coastal systems for a long time, usually from a fisheries or water quality context, and then there was some interest in sea level rise responses. And then suddenly, people started looking at the climate mitigation benefits, and blue carbon took off. And these are like Duarte papers, Chamorro papers. Then green infrastructure started taking off, and now people are starting to use coastal data in global climate models. It's not just a little cottage industry anymore. Because of this whole history, we have a lot to build on, but we haven't been doing it as a community as much as we should have been. So that's really what we try to push forward on in these different projects is what can we say from all those years of data. Some things that are emerging are new theories, and this one I think is an important one. which is that of all ecosystems in the world, there's a positive influence of sea level rise on carbon sequestration in salt marshes or in all tidal marshes in this paper. But to a tipping point, it's not going to keep going. At some point, as sea level rises, accretion will rise to meet that boundary, and then at some point, it's going to start to decline, and that's when you're going to start losing your marshes. And that tipping point is different for every marsh across the United States. This is the problem. We're trying to figure out what the tipping points are. And there's other papers, too, that have actually put boundaries on what those tipping points should be. But ultimately, this is an organizing principle, I think, that is helpful for us to understand the geomorphic context of carbon sequestration and how it's being influenced by sea level rise. Oh, well, this triangle is huge now, but the bottom line is it's an accounting pyramid of the way that the IPCC, for example, documents greenhouse gas fluxes for land use change processes. We were funded by the NASA Carbon Monitoring System, which is an amazingly progressive approach to helping stakeholders understand how carbon fluxes are being affected within their particular sector. And we were focused on getting coastal wetland carbon fluxes into the IPCC National Greenhouse Gas Inventory. That was what we were funded to do. And if you look at the IPCC, you can just use the Tier 1 default values, and those are okay. There's also the idea of using Tier 2, regional or countrywide, the specific your country values. And the third is basically process-based modeling. So understanding, being able to get a finer certainty to your data. We are trying to use as much field data as we can to validate remotely sensed and national data sets like NOAA CCAP, the Coastal Change Analysis Program, like NWI, National Wetland Inventory, like SERGO, the national soil maps. And so we've been trying to link all these together. Sorry, and I should say, again, large team, many federal agencies, many universities, just a really super team to work with. I have to say I'm very happy to see that the EPA did end up going with what NOAA put forward for the first time accounting for coastal wetlands in the National Greenhouse Gas Inventory. So once it's been reported, as it was just reported a couple months ago, we're going to be reporting this forever now because it's been done once. And it was done at sort of a Tier 1/2 level, and we think we can get a little bit better by reducing uncertainty, moving beyond that level. It was done in a tabular form. So basically there's certain numbers that were associated with different land use changes, and we see basically about 12 million metric tons. Oh, sorry. The first thing I should say is that one thing we discovered very quickly is that most of the wetlands are remaining wetlands in the United States. We're not having a whole lot of loss over the last 1990 to 2015, that time frame. We don't have as much loss as you might think. And so wetlands remaining wetlands is a very important term, and so we were able to get credit for this as basically a managed land proxy, the idea that we protect our wetlands, therefore we should get credit for the wetlands. And so just to put this in perspective, this is about a rate of about 3 teragrams for the whole coterminous US per year. That's about 0.2 teragrams of methane release per year. This is, again, using default values, Tier 1. And this is about on par with what Ray was presenting about for the East Coast. It's about twice that for the whole US, that's the rate we have. And they did not do biomass in this particular assay because they just assumed it was 0 because we didn't have data for that. So our goal, again, in the NASA project is to reduce uncertainty. How much tighter can we get the data? And so the first questions are, how uncertain are these national layers? How much better do they need to be to actually then improve the accounting? Where are the biggest data caps? There are regional holes. And then where is our uncertainty? Is it with the monitoring data, or is it with our modeling, sort of a process-based understanding of how to use the data? And so I'm just going to cut to the chase and use the CCAR's red, yellow, green colors to basically say we have high uncertainty where it's red, and we have low uncertainty. We feel pretty confident when it's green. So I can say that after doing this for about you were just coming up on our 3rd year, coming up on the end, we're just about to end it. I think biomass we can do pretty well. Carbon density we can do pretty well. Carbon accretion, you'll see some of the caveats there. But our big problems are the maps and the methane flux. We just don't have a lot of data here. And these maps are really uncertain. And I'd like to see some improvements in that. I think that would help us best with accounting. So I'm just going to step through some of the basic things that we learned in the maps, then the biomass, then the soil, then the methane, and then I'll get to the future thoughts I have. So ultimately, this is about how many million hectares, about 2.8 million hectares of mapped tidal wetlands. That's a conservative estimate. The CCAP is actually all of this green area. CCAP has a lot of coast wetlands in it, but CCAP is not all tidal. To get to how much of that wetland is actually tidal, you have to go to the National Wetlands Inventory where they code it by tidalness, whatever. And basically, of those, about 6% of the country's wetlands are actually tidal wetlands. When you look at how they break out in salinity, most of them are salt marshes, which they call estuarine emergent. That's what we call both CCAP and WI. Freshwater marsh would be palustrine emergent. Mangroves, which would be estuarine forest and shrub. And then freshwater tidal forest, which would be palustrine forest and shrub. So that's sort of the breakout, what they look like. When we look at land cover change, again, we see very little wetland loss in the range that we were able to look at for CCAP, 1996 to 2010. And if we saw any loss, this is actually a log scale to put this in perspective, most of it's to open water. And almost all of it is in Louisiana. So we're losing huge amounts of marsh in Louisiana, and that shows up pretty strongly in the CCAP data set. In fact, this is the CCAP data from our project plotted against the way that USGS does the math. This is Brady Cubion's data. And they're similar, but you can see that most of our data are a little bit below what Brady's estimates would be. So we might be underestimating a little bit of the change. So without belaboring the maps too much, because this is really important for accounting, one of the key things is nobody has taken it upon themselves to make a map of the head of tide, just a tidal zone map. Where's the boundary? And you could do this with mean high water spring tides, which is here we mapped it for the whole US, but there's a lot of uncertainty in there, just to put that in perspective. But we find that when we draw that line and you look at the National Wetlands Inventory, if you're below that line, a wetland below that line ought to be either tidal, or if it's been messed around with, ditched or drained, farmed, or impounded. There should be an effect. But about half of them are just not coded like that at all. So it makes you really question whether we have all the tidal maps perfect or accurate. And we probably have about 1 million hectares still in play that could be tidal that we don't, that we're not accounting for. The errors are just numerous. It's hard to explain all of the varietals, but basically it just looks like differences between approaches and different, who's in charge of that segment versus that segment. And there's other changes too that are hard to follow. This is Blackwater in Chesapeake Bay. This is the California Delta, Sacramento, San Joaquin. Two other maps that I think would be very helpful is a salinity map that wasn't just fresh and estuarine, but actually totally fresh, totally saline, and then some sort of mixed category in the middle, at least something better than the two classes we have right now. And the third is elevation, and actually that in the end is what we think would be the most helpful to almost all sectors of accounting. So I'm just going to step through the biomass and then go into the soil data. These are our 6 sites that we focused on, sentinel sites, where we really put our efforts in to look at uncertainty. And so we've got basically Puget Sound here, San Francisco Bay, Terrebonne, Louisiana, the Everglades near Shark River, CERC, the Smithsonian Environmental Research Center, and then Cape Cod right up here, the National Estuarine Research Reserve in Wacoit Bay. And basically this particular data set I'm just showing, or this picture I'm showing, all these little red plots, this is where we sent people out to measure biomass so that we could come up with a tidal marsh algorithm for mapping biomass using Landsat and NAPE. This is work by Kristen Bird. And what's really amazing is that she found across all of these sites, she was able to eventually do a universal model. And this is what the data looks like for Louisiana. I just want to give you a sense. So we're looking at basically ranges of, in this more saline area, maybe about 50 to 250, and then we're going, as we go up over to Atchafalaya, we get more higher values, like let's say 1,000, 1,500. One of the reasons you see this transition is not just that the biomass per plot is different, but the fraction green within a Landsat plot is a lot less. So these are these fringing marshes that are disappearing. So there's a lot of open water in a given 30-meter pixel. So therefore, from an accounting perspective, you need to remove that, and that's one reason you get this type of a pattern. So again, I want to say to be able to come up with this universal model, we applied it in all these sites, exact same approach. One of the biggest drivers of it was the soil-adjusted vegetation index. It was really the most important, and there was all these spectral bands of importance. We tried radar. It didn't add anything new to it. It actually gave us good results. It just didn't add anything new to the spectral results. What was most important is that the site variability, the site as a variable was not important. We did not find that these were driving the patterns. We could apply a single model everywhere. And so it worked across all sites. These are all the data sort of plotted up, not all the data, but most of the data here plotted up by site. And then you can also see by species type. Most of these have very tall, erect, graminoid type plants. But even when we had a broadleaf plant, we still got a fairly good fit with this map, with this algorithm. So it worked pretty good. And the ultimate bottom line here is that there was a slight difference that the estuarine emergent marsh was a little bit less, about 450 grams per meter squared of biomass, and the palustrine in orange was about 550 on average. But in general, they really weren't that different. The salinity didn't seem to be important to tidal marsh biomass. This here is just the mean and 2 standard deviations off of here. And so what you can just see is that it's actually kind of amazing that you could have such a similar relationship across all these sites. So stock is fairly invariable, what I'm saying, for biomass across the country in terms of an average for a given, for tidal wetlands. That means you could do a tier 1 approach and not be too off. That said, this was done in a totally automated, Landsat-driven, globally applicable way, and you could do much better mapping if you just want to look at a particular site and do it quite well. So I think that the biomass data is really telling us we can do tier 3 if we want, but tier 1 isn't that bad. All right, so let me move to soil stock data. This is James Holmquist. He has been in charge of, he's the postdoc on the project, and he's basically been the big compiler of all these soil cores that so many of, probably a lot of people in this room that I haven't even met yet, but just submitted. I don't even know if I have everybody on the list here. So many soil cores submitted. About 500 of them are from unpublished data. So we're very thankful for all of this data. The bottom line is our data, all of these sites are covered in blue, whereas the NCSS, which is the National Cooperative Soil Service data sets are mostly concentrated here on the East Coast. When we look at all of those soil core data, I think the most striking thing is how consistent they are. So we have all these soil cores from all over the country, and in general, they're all coming to this standard central domain of about 26.5 grams of carbon per cubic meter, so to a meter depth. That's the first thing. The second thing is how consistent it is down core. So you're not having this sort of terrestrial pattern whereby it's high, organic matter is high at the surface and then it decreases. What seems to be happening is in some places it's literally exactly the same as you go down. Megan Gunia here found something very similar, which is the peat looks exactly the same as you go down core. But in a lot of our cores, it's simply the fact that as organic matter decreases, bulk density is increasing. And when you put those two together, you end up getting a very similar number down core. This is pretty big stuff, and it's not, I mean, we've been looking at this data a long time, and I haven't seen a good enough treatment of this and its importance. But one of the key factors of that is that all soils, whether they're mineral to peat, should fall somewhere along this line. And if you're on this line, your soil carbon density is going to be about 0.03. That is actually really similar to what the EPA data set came from the National Wetland Condition Assessment. They had 319 cores across the country, and that's what they came up with is their density. We also think, so the other thing is this is a good guidance for people. So if you have this data set and you have, your data point is up here or down here, you might then want to either check something in your math or write a nature paper. So the other thing is what this really means is that the soil carbon density is starting to saturate at about 0.03. And so once you get about 13% organic matter biomass, that's where you start to have the consistent carbon densities. So we're making an argument that this should be the cutoff for mapping inorganic versus organic soils in the coasts. All right, so if carbon density is so consistent, this applies that the carbon accretion, which is just basically the total amount of carbon that's getting stored in the soil, is ultimately a function of volume. It's the increase in volume. This has been known for a long time. We're in an auditorium named after, I'm guessing, Redfield, and this is old data, theoretical, and this data here is empirical. Again, Megan Gagne has been tracking sea level rise and then plotting against it marsh accretion, and you can see that basically the marshes are accreting in concert with sea level rise, which a little bit more fits and starts, but there's a sort of a smoother curve with sea level rise, with accretion, but it is doing it. So the question is this mappable? And we thought, well, there's tide gauges across the U.S. You know, most of these are down in the like 2 to 3 millimeter zone. Some of these are in the 9 millimeters per year zone. Some of these on the East Coast are in the more 5 millimeters per zone. We should be able to map sea level rise as a way to look at accretion. And what we found is a little bit of a problem because of this difference within the watershed. Some of them are tracking and some of them are not. And I think one of the best data sets I've seen to show this is this new map that just came out from Tornquist's group. And you can see there's 2 tide gauges in Louisiana, and both of them say 9 millimeters per year. But if you look, only in Louisiana could you do this because they have the CRIMS network of all the beautiful SETs out there to measure elevation change, and they're able to show that land subsidence is actually really wonky. It's all over the place and depends on a lot of local variables as opposed to just what you see with the 2 tide gauges. And I'll just point you to these papers that, again, show that because of these CRIMS data, the Coastwide Reference Monitoring Program, you can see some areas sinking, some areas doing just fine, and I just point you to that paper. So let me then just finish the carbon accretion story by saying that is the total pool of carbon being stored. And it's by definition going to include allochthonous, carbons coming in from the outside, and labile carbon, fresh new carbon that's in the system. Carbon sequestration, we have a terminology problem that needs to be solved in our community of all these different terms for storage, burial, accretion, accumulation, and so on. But carbon sequestration ultimately is what markets are after, and that's long-term direct capture, so that what's being produced in site, what's being stored there. And that's a harder one to measure because it's a fraction of what you can actually measure. So what it really needs to be is modeled. So using MEM, this is Jim Morris who developed this model. He basically ran it for virtual marshes, every possible combination of sediment and sea level rise and biomass and so on. And what he found is that we can estimate carbon sequestration pretty well as sea level rises and also by the net biomass the maximum biomass that you find in a given site. And I'm just going to emphasize that within the range of wetland types that we have, this is sort of our happy spot. This is where most sea level rises are falling and most biomasses are falling in terms of max. So you should really expect somewhere between about 40 to 200 grams of carbon per meter squared, and not too much more than that. You're probably looking at this cluster here and this cluster here. and I think the real point here is that a lot of these, when you have short cores, they're a lot younger, so you probably have labile material and potentially allochthonous material in there. And when we talk about short cores, we're also talking about fresher material. These 9 millimeters here, this is the data from Louisiana. And the point here is it's sinking so fast that 20 centimeters in Louisiana, which is a lot of these cores are 20 centimeters, is 20 years, whereas 20 centimeters in California is like 100 years. So there's a time step here that we need to be taking into account when we do this math. All right, I'm just going to finish up with the methane. This is the famous Poffenbarger curve, the most famous undergraduate thesis project ever in my science world. And all of our data are in gray, and you can definitely see this thing where there's no methane emissions until you get to about, she uses the word 18 parts per thousand, and then you start to see all this variability. So Sarah Knox is working at USGS. with me, and she updated this with all new data since 2011. So she put static chamber data in black, and then she put some eddy covariance, because we're starting to get, because of OpenPath, some eddy covariance data in there. And those data are down in here. I'm just going to show some of our data coming from California right now. They're down in here, and we're about 11 parts per thousand zone where we are working. And without going into great detail, we're not seeing a whole lot of emissions from that sort of brackish zone. And we have 3 years running so far. And there's no real difference in the methane emissions between those years. It's very hard to look at a salinity influence right now. Sarah's poster, which actually focuses on CO2, gets at this variability. There's a very strong tidal signal in our data set for CO2. And the fact that we have totally a drought year here and that the wettest year on record here gives us an ability to try to figure out what are the key drivers of carbon cycling in this site. So I pointed to her paper because she's doing some really clever wavelet analysis and so on to get to what are the key drivers of this variability. So what's the future? What does this mean for carbon accounting in tidal wetlands? I'll just say, in general, this is the type of changes that we found. Is the majority of wetlands are these salt marshes, remaining salt marshes. And then we have tidal fresh marshes, remaining tidal fresh marshes. Then we have some mangroves, palustrin, and so on. Ultimately, they're not, our values are going to be pretty similar to what was reported the first time around, but we've narrowed the confidence intervals on it. I want to point out that the big hammer in the room here is this transition from salt marsh to open water. We don't actually have a good value for this, and the default in the IPCC report is basically this many CO2 equivalents. So it's a lot, there's a lot of carbon loss by virtue of this transition. In terms of soil stocks and biomass stocks, there's not a whole lot of regional variation. We're not seeing, we're seeing that we think that the remaining variation is salinity elevation. Accretion is difficult to model because of within basin, high marsh versus low marsh, for example, or other types of problems. And then the key uncertainties for us were the tidal zone map and the methane variability. I'm just going to close by saying that we think elevation is a big driver. If you don't correct your LIDARs, you'll have huge errors up to 22%, 22 centimeters on average. By correcting the LIDAR, James was able to get the elevations from 22% positive bias to 2 centimeters, from 22 centimeters positive bias to 2 centimeters positive bias, and also narrow this, so we improved accuracy and precision by doing correction. And basically, this is the DEM for the CERC G-Crew that was provided by Massachusetts, and it's used in the NOAA sea level rise view, or what everybody uses. This is what it says: monthly tides flood G-Crew. If you actually look at the real elevations, it's actually daily tides that flood G-Crew. We wanted to see, could we model this? We found that we used Kristen's biomass data from the site. We could basically meet some of the assumptions of MEM. And so then he ran MEM on a corrected LIDAR and a non-corrected LIDAR. And you can see that we're already starting at a lower elevation. And you pull this out to 100 years. And basically in the end, after 100 years, to 2100, this has gone totally subtidal, whereas the original LIDAR is telling us that we're still being daily flooded. So there's just this fundamental problem with elevation. There's a positive bias pretty much everywhere. If you see a positive bias, your biggest problem is going to be in microtidal sites. So just think about the Gulf Coast. So if you're off by 22 centimeters on average in your LIDAR, if your total tidal range is only 20 centimeters, you know, it's the difference between life or death. So not so much a problem in these more macro-tidal areas. So I wanted to end this with basically, what does this mean for science? So I'm talking all about accounting, but from science, I think we've found some pretty interesting things. One is just that amazing consistency of soil carbon density with depth and its similarities across the whole country, as if, again, they share more in common with each other than they do eco-regionally. Big questions for us are, why is it saturating, and why are compaction and decomposition happening basically at the same rates? One of my proposals is that we basically start to accept that burial as a term is a geomorphic process as opposed to a biogeochemical process first. it's a geomorphic process, so it's somewhat constant. It's probably variable with sea level rise. We might not be able to track that every year because sea level rise is so variable, but maybe more of a decadal scale. And then I'm going to propose that lateral flux is just going to be proportional to NEE based on once you've removed that burial term. So just conceptually what that would look like. Small burial, big would have a small effect on lateral flux, whereas big burial might have a larger effect on lateral flux. And this is differences between years. So you can have lots of protection versus little protection and so on. And then, what does this mean for the future? I think we have a lot of exciting work to do. I hope that excites people as much as it does me, because I just see us total job security, even in this climate, because this is it's so new and exciting. So thank you.